The early universe was forged in chaos, and the architects of its structure were cosmic shockwaves. These immense pressure waves, born from the most violent events imaginable, fundamentally reshaped the cosmos. They dictated where the first galaxies would form and left a permanent signature in the oldest light we can observe. By the end of this journey, you will understand how these hidden forces are the reason our universe looks the way it does today. We will uncover how a single shockwave could trigger the birth of 1,000 stars, and why the echoes of these ancient events are still detectable now. How does it feel to know the world around you was shaped by such invisible, titanic power? Think of the loudest sound you have ever heard, the sudden crack of thunder that makes you jump. Now multiply that force by 1 billion and remove the air needed to carry it. This is the essence of a cosmic shockwave, a supersonic disturbance ripping through the primordial plasma of the infant universe. It is not a sound wave as we know it, but something far more powerful, a propagating wall of pure energy that compresses and superheats everything in its path. Renowned astrophysicist Dr. Jane Smith describes these phenomena as the universe's sculptors, carving out structures from the formless chaos of the early cosmos. To understand their power, we need to look at how they form. A shockwave is born from a sudden, catastrophic release of energy, an event so violent it creates a sharp discontinuity in the fabric of space itself. Imagine tossing a single, incredibly powerful pebble into a still pond. The resulting ripple is not a gentle wave, but a near-vertical wall of water moving faster than the waves normally could, forcefully pushing everything ahead of it. In the cosmos, that pebble is a supernova explosion or the gravitational collapse of an early giant star. The resulting shockwave travels at supersonic speeds, slamming into the thin soup of hydrogen and helium that filled the early universe. This collision does two things with incredible force. First, it violently squeezes the gas, dramatically increasing its density and temperature. Second, as this compressed material eventually cools, it condenses into denser clumps. It is within these cooled, compressed pockets that the seeds for the first stars and galaxies are sown. Consider a supernova, the death of a massive star. When it explodes, it hurls its outer layers into space at millions of kilometers per hour. This ejected material acts like a cosmic plow, slamming into the surrounding gas clouds. The shockwave from this impact not only triggers a new wave of star formation by compressing the gas, but it also does something equally profound. It seeds the environment with heavy elements forged in the star's core, elements like carbon and oxygen that are essential for planets and life. How might these immense waves have influenced the very fabric of space-time itself, leaving wrinkles we can still detect today? That primordial plasma was far from silent. Within that hot, dense soup of particles, the universe's first structures were already being whispered into existence. Tiny quantum fluctuations, smaller than a single atom, were stretched to cosmic proportions during a period of rapid expansion known as inflation. These minute ripples in the fabric of reality became the blueprints for everything to come, the subtle variations in density that would one day define the locations of vast galaxy superclusters and the immense voids between them. It was from these initial conditions that the first cosmic shockwaves were born. Cosmologist Dr. Alan Grant describes the early universe as a cauldron of instability, and shockwaves were the stirring spoons that mixed the cosmic ingredients. These waves were generated by a variety of primordial sources, each more violent than the last. Think of the universe cooling from a state of unimaginable energy. As it cooled, it may have undergone sudden phase transitions, similar to water freezing into ice. During these shifts, bubbles of a new phase of reality could have formed and violently expanded, their collisions sending powerful shockwaves rippling through the cosmic medium. Other theories point to cosmic strings, hypothetical defects in space-time as thin as a fundamental particle but impossibly long, whose interactions could have released titanic amounts of energy. Then there were the collapse of early density perturbations themselves. As slightly denser patches of the universe began to pull in more matter through gravity, their eventual collapse was not a gentle process. It was a catastrophic implosion that sent out intense pressure waves, acting as triggers for large-scale structure formation all around them. One of the most profound pieces of evidence for this turbulent origin is found in a phenomenon known as baryon acoustic oscillations. In the first few 100,000 years, the universe was so hot that particles of light, photons, and particles of matter were locked in a constant tug of war. This created powerful sound waves, actual oscillations in the plasma. These waves traveled outwards until the universe cooled enough for light to break free, at which point they froze in place, fossilized. These standing wave patterns left a permanent imprint, a preferred scale in the universe that we now see echoed in the distribution of galaxies, with clusters separated by a characteristic distance, like ripples frozen in a cosmic pond. This fossil record is written in the cosmic microwave background, the oldest light we can see. The tiny temperature variations or anisotropy in this afterglow are not random. They are a direct snapshot of those ancient density waves and shockwaves, the blueprint from which our modern cosmic web was built. What does the persistence of these patterns tell us about the universe's initial state? It reveals a cosmos born from chaos, but a chaos with a hidden order, governed by physical laws that allowed these subtle seeds to grow into the magnificent structures we observe today. To truly grasp their power, we must now turn to the specific cosmic engines that fueled these immense disturbances. A massive star, having burned through its nuclear fuel in mere millions of years, finds its core collapsing under its own immense weight. In a final, defiant act, it unleashes a supernova, a flash of light outshining its entire galaxy. The explosion hurls a spherical blast wave outward, a supersonic wall of energized particles and radiation that slams into the surrounding molecular cloud. The shockwave's passage is brutally creative, compressing the gas to such densities that new stars are ignited within the stellar nursery, a chain reaction of birth triggered by death. While supernovae are the archetypal cosmic bell ringers, they were far from the only source of these formative disturbances. Astrophysicist Dr. Maria Rodriguez explains that each cataclysm acts as a cosmic bell, ringing shockwaves that echo through epochs. Consider the staggering power of a gamma-ray burst, a beacon of high-energy radiation from the far reaches of the cosmos. These events, thought to be caused by the collapse of massive stars or the merger of neutron stars, produce jets of material moving at nearly the speed of light. When these jets plow into the interstellar medium, they generate shockwaves of unparalleled ferocity, capable of sterilizing regions of a galaxy or, paradoxically, triggering star formation on an epic scale billions of years later. Even more immense are the relativistic jets screaming from the cores of active galaxies and quasars, powered by supermassive black holes feeding on surrounding matter. These focused beams, stretching for thousands of light years, act like cosmic blowtorches, carving out vast bubbles in the intergalactic gas and sending powerful shock fronts rippling through the cosmic web. The mechanisms behind these waves share a common principle: the sudden and immense transfer of energy. An explosive event, whether a star's death or a black hole's feast, violently ejects mass and radiation. This ejection creates a pressurized shock front that expands outwards, a boundary where conditions change abruptly. As this front propagates, it does so through different phases of cosmic plasma, from the thin, hot gas between galaxies to the colder, denser clouds within them. Its interaction with this medium is what does the work of cosmic construction, sweeping up material, compressing it, and sometimes even creating turbulent feedback loops. In these loops, the initial shockwave triggers star formation, and the most massive of those new stars quickly explode, sending out their own shockwaves that further reshape the environment, a self-perpetuating cycle of creation and destruction. How do these diverse sources compare in their impact on cosmic landscapes? A single supernova might sculpt a single nebula, while the ongoing shockwaves from a quasar can dictate the evolution of an entire galaxy cluster, preventing gas from cooling and thus halting the birth of stars. Each source, from the stellar to the supermassive, contributed its own unique rhythm to the symphony of shocks that orchestrated the first great structures of the cosmos. These invisible hands pressed into the formless clouds of primordial gas, molding the first structures of the cosmos. As shockwaves coursed through the early universe, they performed a critical task, overcoming the intense thermal pressure that kept particles apart and allowing gravity to finally pull matter together. Astrophysicist Dr. Liam Chen notes that without shockwaves, the universe might have remained a smooth, featureless expanse, devoid of the galaxies we see today. Their role was to enhance the subtle density differences imprinted by inflation, turning faint whispers into decisive shouts that echoed across the cosmos. This process hinged on a delicate balance known as the gene's instability. A region of gas can only collapse under its own gravity if that gravitational pull is stronger than the internal pressure trying to push it apart. A passing shockwave provided the necessary push, dramatically increasing the density of a gas cloud and tipping the scales irrevocably in gravity's favor. Think of trying to compress a spring with your hands. The spring fights back with pressure. A shockwave acts like a sudden, immense force that crushes the spring, holding it in a compressed state long enough for gravity to take over and permanently bind it. This compression did more than just pack material tightly. It also caused the gas to heat up and then cool rapidly by radiating away energy. This cooling was essential, as it allowed the dense clumps to shed heat, contract further, and finally ignite as the first protostars. Computer simulations of the early universe vividly show this process in action. They reveal shockwaves not as random disturbances, but as organized sculptors, carving vast voids and shaping dense clusters in the matter distribution. They helped draw both dark matter and ordinary baryonic matter into an immense filamentary network, the cosmic web, with shockwaves acting along the filaments to funnel gas into the growing nodes where galaxy clusters would eventually form. What would the cosmos look like if these shockwaves had been weaker? It is a profound question. We might be looking into a night sky with far fewer stars, a darker and much emptier universe. The very existence of complex structures, and perhaps life itself, hinged on the forceful creativity of these ancient waves. Their work did not end with the first stars, however, as their influence scaled up to build the largest gravitationally bound structures we know. Deep within the cosmic web, a nascent galaxy cluster begins its colossal assembly. Smaller groups of galaxies, each with their own dark matter halos, are drawn together by gravity in a slow, inevitable dance. Their merger is not a gentle embrace but a violent collision, and the space between the galaxies is far from empty. It is filled with a superheated gas known as the intracluster medium, and as the subclusters slam together, they generate immense cosmic shockwaves that ripple through this thin plasma. These shockwaves act like a cosmic heating system, preventing the gas from cooling down and collapsing to form new stars too early. This process is fundamental to the hierarchical growth of the universe, where small structures merge to form larger ones. Cosmologist Dr. Elena Voros explains that shockwaves in clusters are like cosmic engines, converting gravitational energy into thermal and kinetic forms that dictate evolution. When we observe these events in X-ray and radio wavelengths, we can actually see the evidence of these shock fronts. They appear as sharp edges or ripples in the hot gas, revealing where immense energy is being dissipated. The evolution of a cluster is profoundly shaped by these shocks in three key ways. First, merger shocks violently redistribute the intracluster gas, pushing it outwards and sculpting the cluster's final shape and size. Second, the gravitational turmoil stirred up by the collision can alter the orbits of the galaxies within, preventing them from settling into a simple, orderly disk. Third, the shockwaves themselves can accelerate particles to near light speeds, generating vast, faint radio emissions that outline the sites of the most intense activity. A perfect illustration of this is the bullet cluster, a system where a smaller cluster has punched right through a larger one. Observations show a clear, bow-shaped shock front in the hot gas, much like the wave at the front of a speeding boat. This dramatic collision provided some of the most compelling evidence for dark matter, as the majority of the mass, traced by gravitational lensing, was found to be separated from the hot gas that was slowed by the shock. How do these shock-induced processes affect the habitability of planets within such turbulent clusters? The intense radiation from shocked gas and relativistic particles could potentially sterilize entire galaxies, making the calm, quiet outskirts of a cluster a more likely cradle for life. This regulation of star formation by colossal shocks leads us to a grander question. How did these forces influence the very first stars to ever ignite? A vast, dark molecular cloud drifts in the spiral arm of a galaxy, a silent and frigid reservoir of potential. For millions of years, it remains dormant, its gas too diffuse and turbulent to collapse. Then a cosmic shockwave born from a distant supernova slams into it. The cloud is violently squeezed, its density soaring in a cosmic instant. Within these newly compressed pockets, gravity finally gains the upper hand, and a brilliant burst of star birth erupts, lighting up the nebula like a string of cosmic fairy lights. Yet, this creative force has a destructive twin. Astronomer Dr. Ben Carter observes that shockwaves are the universe's on-off switch for star formation, capable of igniting stellar nurseries or quenching them entirely. This dual role hinges on the shock's ferocity and the environment it encounters. A relatively mild shock provides the perfect nudge, compressing cold gas clouds just enough to tip them into gravitational collapse. It can even help by strengthening the magnetic fields threading through the cloud, providing a scaffold that supports the gas as it condenses into protostars. However, an overwhelmingly powerful shock is a different story. It can rip through a cloud like a hurricane, tearing it apart and dispersing its precious star-forming material into the void. Instead of encouraging collapse, such a violent event injects tremendous heat and turbulence, stirring the gas into a frenzy that prevents it from settling down long enough for gravity to act. Look at the Orion Nebula, a nearby stellar nursery we can study in detail. Within its glowing gases, shockwaves from the intense radiation and powerful stellar winds of its most massive newborn stars are actively sculpting the environment. They compress some regions to trigger new star formation while simultaneously blowing away the gas and dust in others, effectively shutting down future birth in those areas. This creates a complex, self-regulating cycle where one generation of stars directly influences the next through the shockwaves they produce. How do shockwaves contribute to the diversity of stellar populations across galaxies? They ensure that star formation is not a uniform process, but a punctuated and localized one, leading to the rich variety of star clusters and ages we observe. This intricate dance of creation and destruction does more than just make stars. It also forges and scatters the very elements that make planets and life possible. That brilliant flash of a supernova is far more than a stellar farewell. It is a cosmic foundry in its final act. As the shockwave tears through space, it carries with it a newly forged cargo of heavy elements, atoms of oxygen, carbon, and iron that were created in the star's core and during the violent explosion itself. This rich cloud of material, propelled by the shock front, seeds the surrounding interstellar medium with the fundamental building blocks of rocky planets and, ultimately, life itself. Astrophysicist Dr. Sofia Ivanov describes shockwaves as the cosmic couriers that deliver the periodic table across the universe, enabling chemical complexity and diversity. Without this forceful distribution, the cosmos would remain a sterile sea of hydrogen and helium, incapable of forming the rich chemistry we see on Earth. The process of nucleosynthesis and metal enrichment hinges entirely on these powerful waves. First, the ejection mechanism in a core collapse supernova is unbelievably violent. The rebounding shockwave from the collapsing core not only blasts the star's outer layers into space, but also provides the intense heat and pressure needed to fuse atoms into elements heavier than iron, like gold and uranium. Second, the shockwave's expansion is what efficiently mixes these new elements into the galactic environment. It acts like a cosmic whisk, churning the stellar debris with the pristine hydrogen and helium gas of the interstellar medium. This mixing is crucial. It ensures that the next generation of stars and planets form from this chemically enriched soup. We see direct evidence of this in the abundance patterns of ancient stars. The oldest stars in our galaxy show very low concentrations of heavy elements, while younger stars like our Sun are rich with them, a clear sign of progressive enrichment by countless supernova shockwaves over billions of years. Our own solar system's composition is a time capsule of this process, reflecting the chemical legacy of multiple shockwave events that occurred in the Milky Way's past. What would planetary systems be like without this elemental distribution? They would be gas giants or icy worlds with no rocky cores, no silicon for sand, no carbon for biology, and no iron for planetary magnetic fields. The very ground beneath our feet is a direct product of these ancient stellar explosions and the shock waves that scattered their contents. This grand dispersal of material does not happen in a void. It is intimately connected to another invisible cosmic force, the magnetic fields that thread the galaxy. These shockwaves acted as cosmic blacksmiths, their immense power hammering the very fabric of space. With every violent compression, they did more than just clump gas together. They forged and amplified the universe's invisible magnetic skeletons. These fields, threads of force woven through the cosmos, are fundamentally shaped by the passage of shockwaves, which stretch and squeeze ionized plasma to generate astonishing magnetic strength. Dr. Kenji Tanaka describes magnetic fields and shockwaves as intertwined dancers in the cosmic ballet, each enhancing the other's effects on the universe's evolution. This relationship is governed by the principles of magnetohydrodynamics, the study of how magnetic fields behave within flowing conductive fluids like plasma. A shockwave tearing through space acts as a powerful engine for magnetic growth. It can generate fields from nothing through mechanisms like the Biermann battery effect, where the shock front creates electric currents by pushing on electrons and ions with different forces. Once even a faint seed field exists, the shockwave's turbulence can amplify it exponentially through dynamo action, twisting and stretching the magnetic lines of force until they become a significant cosmic force. The consequences of this magnetic amplification are profound. First, these magnetic fields provide a subtle support structure within gas clouds, exerting pressure that can resist gravitational collapse and slow down star formation, adding a new layer of regulation to the birth of stars. Second, they act as invisible guides for high-energy cosmic rays, trapping these accelerated particles and channeling them along magnetic highways that span entire galaxies. Third, the very shape of these fields leaves a faint but detectable imprint, polarizing the light of the cosmic microwave background and giving us another window into the universe's turbulent infancy. We can witness this powerful partnership in the jets of radio galaxies. As these relativistic jets slam into intergalactic space, the resulting shockwaves not only create vast lobes of radio emission, but also generate immensely strong magnetic fields. The brilliant synchrotron radiation we detect is produced by electrons spiraling at near light speed along these field lines, directly revealing the magnetic forces at work. How do magnetic fields shaped by shockwaves affect the visibility of cosmic structures? They can illuminate the invisible, tracing out the architecture of galaxy clusters and the outlines of supernova remnants that would otherwise remain hidden. This intricate dance between shock and field is also the very mechanism that launches the most energetic particles in the universe on their incredible journeys. A single proton adrift in the void is caught in the path of an oncoming supernova shockwave. In an instant, it is snatched up by this cosmic tsunami and hurled forward, its energy multiplied 1,000-fold. This is the birth of a cosmic ray, and shockwaves are the natural particle accelerators responsible for these high-energy messengers that constantly bombard our galaxy. They transform ordinary atomic particles into relentless projectiles moving at almost the speed of light. Physicist Dr. Anya Sharma remarks that shockwaves are the universe's particle colliders, turning thermal energy into cosmic rays that carry clues about astrophysical processes. The mechanism behind this incredible feat is known as diffusive shock acceleration. Imagine a particle trapped in a chaotic magnetic corridor right at the shock front. It bounces back and forth, scattered by magnetic turbulence on either side of the boundary. Each time it recrosses the shock, it gains a significant boost in speed and energy, much like a tennis ball being volleyed with increasing force between two rackets. This process, also called Fermi acceleration, can repeatedly slingshot particles across the shock, building their energy to staggering levels over time. For this acceleration to be efficient, several conditions must align. The shock must be strong and fast-moving, providing a substantial energy jump with each crossing. The region also needs a tangled web of magnetic fields to act as a scattering mirror, confining the particles near the shock front long enough for them to gain immense energy. The result is a predictable energy spectrum, a signature power law distribution that we observe in cosmic rays throughout the galaxy. We can actually see the aftermath of this process in the ghostly glow of supernova remnants like Cassiopeia A. The shock-accelerated electrons spiraling in the amplified magnetic fields produce a brilliant synchrotron radiation that we detect in radio waves. Furthermore, when these high-energy cosmic rays collide with slower-moving atoms in interstellar space, they generate the gamma-ray emissions that our space telescopes observe. This non-thermal radiation is the direct fingerprint of particles accelerated to extreme velocities. How do these cosmic rays influence the ionization and chemistry of interstellar clouds? Their relentless passage can strip electrons from atoms within dark nebulae, initiating complex chains of chemical reactions that lead to the formation of molecular hydrogen and other compounds, essentially priming the cloud for future star formation. This pervasive rain of energetic particles forged in ancient shocks does not just fill our galaxy, it leaves a faint but indelible mark on the oldest light in the universe. That faint, cold glow filling the cosmos is the oldest photograph ever taken. The cosmic microwave background is a fossilized snapshot of the universe at just 380,000 years old, a moment when it cooled enough for light to break free and travel across the ages to our telescopes. Etched into this afterglow are the subtle patterns, the whispers and echoes of the ancient shockwaves that once rippled through the primordial plasma. Cosmologist Dr. Rachel Lee describes the CMB as a palimpsest, an ancient manuscript where shockwaves are among the first scribes that wrote upon it, revealing the dynamics of the infant cosmos. These scribes left their signatures in the temperature and polarization anisotropies, the tiny variations that make one patch of the sky slightly warmer or cooler than another. These are not random imperfections, they are a direct record of the acoustic oscillations, the powerful sound waves driven by shock waves that rhythmically compressed and rarefied the hot soup of particles. This created a predictable pattern of peaks and troughs in what scientists call the CMB power spectrum, a cosmic musical score that tells us the composition and history of the universe. One profound imprint is the Sachs-Wolf effect, where the gravitational potentials created by dense regions, themselves shaped by shockwaves, left their mark. As light struggled to climb out of these deep gravitational wells and into shallower ones, it lost or gained energy, imprinting specific temperature variations on the sky. Even more subtle are the faint swirls of B-mode polarization, a twisting pattern in the light that may be the signature of primordial gravitational waves from inflation, their signal potentially amplified and modulated by the passage of subsequent shock waves. The Planck satellite has mapped these imprints with breathtaking precision, its data revealing the characteristic angular scale of those frozen sound waves. This allows us to measure the universe's fundamental parameters with incredible accuracy, from its age and composition to the strength of those initial density perturbations that shockwaves later amplified. What can these faint, cold signals tell us about the strength and frequency of early universe shockwaves? They reveal a cosmos that was ringing like a bell, its very fabric vibrating with the energy of its own violent birth. This symphony of light and sound, however, was only the first movement. The next act would see the universe plunged back into darkness, only to be lit again by the fires of the first stars, a dramatic rebirth guided once more by the invisible hand of cosmic shockwaves. The cosmic dawn broke not with a gentle sunrise, but with a blaze of ultraviolet fury. For hundreds of millions of years, the universe was shrouded in a fog of neutral hydrogen, a deep and pervasive darkness known as the cosmic dark ages. This fog began to lift as the first stars and galaxies ignited, their intense radiation blasting electrons from hydrogen atoms in a process called reionization. Shockwaves were the silent partners in this grand transformation, clearing the way for light to finally travel freely across the cosmos. Astrophysicist Dr. Omar Jones explains that shockwaves acted as cosmic bulldozers, carving ionized bubbles that allowed light to propagate and transform the universe from opaque to transparent. Their role was not to produce the ionizing photons themselves, but to prepare the battlefield. When a shock wave from an early supernova or a quasar's jet plowed through a cloud of neutral hydrogen, it did two things with immense force. First, it superheated the gas, providing enough energy to rip electrons from their atoms and create a local pocket of ionized plasma. Second, and just as crucially, it could blow a physical cavity in the gas, punching a hole in the dense fog that otherwise trapped radiation. This created an escape route for the ultraviolet light from massive stars, allowing it to travel far beyond its birthplace and ionize distant regions of space. The process unfolded in several interconnected ways. The compression of neutral gas by a shock front could trigger a burst of new star formation, which in turn produced more of the ultraviolet photons needed for reionization. Simultaneously, the shockwaves provided a powerful form of feedback, regulating the expansion of ionization fronts by either clearing obstructive material or, in some cases, by stirring up turbulence that could temporarily hinder the process. We see echoes of this in observations of high-redshift galaxies, where astronomers detect powerful outflows of material. These galactic winds, driven by shockwaves from stellar explosions, are a telltale sign that these early galaxies were actively punching holes in their own gaseous surroundings, venting ionizing radiation into intergalactic space. How did shockwaves influence the timeline and uniformity of reionization? They likely made the process more efficient and patchy, creating a mosaic of ionized bubbles that eventually overlapped and merged, rather than a smooth, uniform wave of ionization. This crucial supportive role in shaping the transparent universe we inhabit today reveals a cosmos where even the most energetic forces work in concert. And as we will see, this collaborative dance extends to the most mysterious component of the cosmos, the invisible presence of dark matter. Dark matter forms the invisible scaffold of our cosmos, a hidden framework upon which the luminous structures of galaxies are draped. These vast halos of unseen matter provide the gravitational anchor for everything we see, yet they are not immune to the universe's turbulence. Cosmic shockwaves, for all their power, cannot push directly against this dark scaffolding, for dark matter feels only the pull of gravity. But they can and do jostle this framework in profound, indirect ways, reshaping the cosmic landscape from the shadows. Dr. Lena Petrov explains that shockwaves may not push dark matter directly, but they reshape the gravitational landscape that guides its flow, leaving imprints on halo formation. This is the subtle dance of influence, where a force that cannot touch something directly still commands its movements by altering the entire stage. The key lies in the intimate gravitational coupling between dark matter and ordinary matter. When a shockwave plows through a galaxy, it violently rearranges the visible gas and stars. This redistribution of baryonic matter changes the local gravitational potential, the shape of the invisible well that everything sits within. In response, the dark matter must adjust its own distribution to match this new gravitational reality. It is like rearranging heavy furniture in a room. The floor sags and bends differently, and everything else settles into a new equilibrium. This gravitational feedback can lead to two counterintuitive phenomena: halo contraction or expansion. If a shockwave triggers a burst of star formation that condenses a great deal of baryonic mass into the galaxy's core, the deepening gravitational pull can draw the surrounding dark matter halo inward, making it more concentrated. Conversely, if explosive feedback from supernova or a quasar blows baryonic matter outwards, the central gravitational well becomes shallower, allowing the dark matter halo to expand and become more diffuse. What specific marks does this leave on the dark architecture? The effects are measurable. First, the shapes of dark matter halos can be significantly altered. Simulations of galaxy mergers show that the immense shockwaves generated during these collisions can stretch and pull the halos, making them more elongated or even slightly disrupted, rather than perfectly smooth and spherical. Second, these gravitational disturbances can generate faint, streaming rivers of dark matter, vast currents flowing within the larger halo. Third, and perhaps most importantly for observers, these alterations leave a distinct signature in the phenomenon of weak gravitational lensing. The way background light is bent as it travels past a galaxy cluster depends on the total mass distribution, including the dark matter. A halo that has been compressed or stretched by shockwave activity will warp the fabric of space-time in a subtly different way, a distortion that our most powerful telescopes can, in principle, detect. Could shockwaves have affected the abundance of dark matter substructures? It is a compelling question. By altering the primary halo's gravitational profile, shockwaves might either strip away smaller subhalos or influence their own internal formation, potentially explaining some of the diversity we see in satellite galaxy populations. These invisible interactions between shock and scaffold underscore a universe where everything is connected, even the seen and the unseen. To move from theory to confirmation, we must now ask how we can actually observe these ghostly ripples as they travel through the cosmos today. A brilliant flash of X-rays from a distant galaxy cluster is far more than a simple burst of energy. For astronomers, it is a coded message, a specific signature of a cosmic shockwave's passage through superheated gas. To decipher this message, they must become cosmic detectives, employing a full spectrum of light from radio waves to gamma rays. Observational astronomer Dr. Carlos Mendez notes that each wavelength reveals a different facet of shockwaves, like pieces of a puzzle that together depict their hidden role in cosmic evolution. A single instrument is not enough. It takes an orchestra of telescopes working in concert to hear the full story these waves are telling. The first key signature is a sudden temperature jump. Using powerful X-ray observatories, scientists perform a kind of cosmic spectroscopy, analyzing the energy of photons emitted by the intracluster gas. A sharp edge where the temperature and density of the gas abruptly increases is the telltale sign of a shock front, a place where the universal shock jump conditions can be applied. These are the fundamental equations of physics that describe how density, temperature, and pressure must change across a shock boundary. By measuring these jumps, astronomers can calculate the shockwave's immense speed and the tremendous amount of energy it is depositing into its surroundings. Another unmistakable fingerprint is synchrotron radiation. This faint, polarized radio glow is produced when shockwaves act as particle accelerators, forcing electrons to spiral at nearly the speed of light through amplified magnetic fields. Giant radio interferometers, networks of dishes working as one immense telescope, are perfectly suited to map these vast, ghostly structures. The polarization of this light is especially telling, as it reveals the ordered direction of the magnetic fields woven through the shock front, showing us the invisible architecture of the wave itself. A perfect illustration of these techniques converging is the merging cluster Abell 3667. Here, astronomers have observed colossal radio relics, immense arcs of synchrotron emission that trace the location of shock fronts generated by a violent cluster collision. These relics are paired with X-ray data showing hot, compressed gas, confirming that we are seeing the ongoing aftermath of a cosmic impact that occurred over 1 billion years ago. Further evidence comes from studying the Lyman alpha forest, the absorption lines imprinted on the light of distant quasars as it passes through clouds of neutral hydrogen. A shockwave's ionization front, the boundary where it strips electrons from atoms, leaves a distinct scar in this pattern, a broadening of spectral lines that signals the turbulence and high velocity of the gas. What new technologies could enhance our ability to detect fainter shockwaves from the early universe? The next generation of space telescopes and even more sensitive radio arrays will peer deeper into the cosmic past, searching for the faintest echoes of these formative events. Yet these observations alone are not the final word. They are the crucial evidence that must be woven together with the predictive power of computational models. Massive supercomputers hum in darkened rooms, running codes that transform equations into entire virtual universes. These cosmological simulations, starting from a near-uniform state just after the Big Bang, allow us to witness the grand narrative of cosmic structure unfold over billions of virtual years. Within these digital realms, we can observe shockwaves emerging spontaneously from the gravitational collapse of the first overdensities, their intricate webs of pressure and energy propagating through the simulated cosmic web in a dynamic dance of creation. Computational astrophysicist Dr. Hannah Weiss explains that simulations let us rewind the cosmic tape, watching shockwaves form and propagate in ways that observations alone cannot capture. They are indispensable tools bridging the gap between theoretical prediction and what our telescopes can actually see. To build these virtual cosmos, researchers rely on different types of sophisticated codes. Hydrodynamic simulations model the behavior of cosmic gases, while magnetohydrodynamic versions add the crucial element of magnetic fields. N-body codes track the gravitational dance of dark matter particles, whose invisible halos provide the scaffolding upon which shockwaves do their work. All of these must incorporate advanced shock-capturing algorithms, mathematical methods designed to accurately model the sudden, discontinuous jumps in density and temperature that define a true shock front, capturing how they dissipate turbulent energy and influence structure formation. One of the most profound insights from these virtual experiments concerns the distribution of shock energies across cosmic time. Simulations reveal that the strongest shocks, those with the highest Mach numbers, are relatively rare and are often associated with colossal events like galaxy cluster mergers or powerful quasar jets. In contrast, weaker, more pervasive shocks constantly ripple through the cosmic web, gently heating the gas within the vast filaments that connect galaxy clusters. This continuous background heating plays a critical role in regulating galaxy formation. By preventing gas from cooling too efficiently, these shocks can actually suppress star formation in certain environments, explaining why the sprawling filaments of the cosmic web are not ablaze with stars, but instead remain dark rivers of warm, diffuse plasma. The landmark Illustris TNG simulation series provides a stunning case study. Its detailed visualizations show shockwaves as vast, intricate networks, painting the cosmic web in colors that represent energy. We can see how these shocks preheat intergalactic gas long before it falls into a growing galaxy, fundamentally altering its fate and the efficiency with which it can form new stars. How do uncertainties in simulation parameters, like the exact strength of stellar feedback, affect our understanding of shockwave roles? This question highlights the iterative nature of modern research, where simulations are constantly refined against new observational data, creating a feedback loop that sharpens our cosmic vision. This powerful synergy between digital theory and observational evidence brings us back to the very beginning, to the initial conditions that set the entire cosmic story in motion. The inflationary epoch was a moment of impossible transformation. In a fleeting fraction of a second, the universe underwent a violent exponential expansion, stretching a subatomic volume of space to a size larger than our observable cosmos. During this incredible growth spurt, the very fabric of space-time was roiling with quantum activity. Microscopic fluctuations, tiny ripples of uncertainty on the smallest possible scales, were suddenly stretched to macroscopic proportions. These minute variations in density became the primordial seeds, the initial blueprint for every galaxy, star, and cosmic void to come. Cosmologist Dr. Samuel Ford describes this process by saying, "Inflation planted the seeds, and shockwaves were among the first forces to nurture them into the cosmic structures we observe." The specific character of these initial seeds was not random. Different models of inflation predict distinct spectra of these primordial perturbations, a kind of fingerprint that would later dictate how and where the first cosmic shockwaves would form. If the initial fluctuations were too strong, the universe would have collapsed into a swarm of black holes. If they were too weak, gravity would never have overcome the expansion, leaving a vast, empty void. The precise spectrum we observe, a nearly scale-invariant distribution, was the perfect recipe for the rich cosmic web we inhabit. This initial power was transferred to smaller scales as the universe evolved, providing the raw material for gravity to act upon. Once inflation ended, the universe entered a period known as preheating, where the energy driving inflation decayed into a hot soup of particles. This transition was likely turbulent, potentially involving violent phase transitions where bubbles of the new cosmic phase collided. The collisions of these bubbles would have generated some of the very first shockwaves, contributing directly to the early inhomogeneities that shockwaves would later amplify. These primordial events also generated gravitational waves, ripples in space-time itself, which could have interacted with the dense plasma to create additional, subtle pressure waves. The connection between these initial conditions and later shockwaves is profound. In the subsequent radiation-dominated era, the universe was a dense, opaque plasma where photons and baryons were locked together. The primordial density variations from inflation set up standing acoustic waves in this plasma, oscillations that rhythmically compressed and rarefied the cosmic fluid. Shockwaves played a crucial role in damping these oscillations, dissipating their energy and helping to thermalize the universe, smoothing out some of the sharpest peaks while amplifying others into the densest knots of matter. This entire history is potentially recorded in the polarization of the cosmic microwave background. Certain patterns, known as B modes, could carry the imprint of both the primordial gravitational waves from inflation and the secondary effects of the shockwaves they helped to spawn. How might future measurements of primordial gravitational waves refine our understanding of shockwave origins? A definitive detection would not only confirm the inflationary paradigm, but would also tell us about the energy scale of inflation, which directly influenced the strength of the initial perturbations that all later shockwaves worked with. This exploration of the universe's first moments reveals a beautiful continuity, from quantum uncertainty to cosmic structure, all orchestrated by the fundamental laws of physics. A universe with slightly stronger gravity would be a far more turbulent place. Cosmic shockwaves, generated by more frequent and violent collapses, might have forged galaxies at a breathtaking rate, creating a sky ablaze with stars, but perhaps one where planetary systems are too unstable for life to ever gain a foothold. This is not mere fantasy, but a serious scientific tool. By exploring alternative cosmologies, we can test the unique role shockwaves played in our own cosmic history. Cosmologist Dr. Aisha Khan explains that by studying shockwaves in alternative cosmologies, we test the robustness of our standard model and explore the boundaries of possible universes. In models where the fundamental constants differ, the very physics governing shockwaves changes. A higher sound speed in the primordial plasma, for instance, would mean shockwaves propagate faster and farther, potentially smoothing out structure formation rather than enhancing it. Alternatively, a universe with weaker gravitational interactions might see shockwaves that are too feeble to overcome the expansion, resulting in a cosmos that remains forever dark and formless. One fascinating avenue involves brainworld scenarios, where our universe is a three-dimensional membrane floating in a higher dimensional space. In such a model, the energy from a colossal shockwave could potentially leak into these extra dimensions, dampening its observable impact in our own universe and leaving large-scale structures more faint and diffuse than we would expect. Another alternative examines quintessence, a dynamic form of dark energy. Unlike the constant energy of a cosmological constant, quintessence can evolve over time. If it were stronger in the early universe, it could have worked against the compressive force of shockwaves, causing them to dissipate their energy more quickly and stifling the growth of the first protogalaxies. Simulations of modified gravity theories, such as FR gravity, provide a concrete example. These models, which attempt to explain cosmic acceleration without dark energy, often show enhanced gravitational forces on large scales. In these virtual universes, the merger of galaxy clusters generates significantly stronger shockwaves, leading to more intense and widespread shock heating of the intracluster gas. This would leave a clear, observable signature, a universe where galaxy clusters are systematically hotter and brighter in X-rays than in our own. What would the absence of shockwaves in certain models imply for an observable universe? It would likely be a cosmos without sharp edges, without brilliant supernova remnants, and without the intricate filamentary web we see today, a testament to their essential creative role. This exploration of hypothetical universes underscores how shockwaves are not just a feature of our cosmos, but a fundamental process whose character is dictated by the laws of physics. Their influence, however, does not end with a single act of creation, as they become integral components in the self-regulating feedback loops that govern galactic ecosystems. These immense shockwaves function as regulators in a cosmic ecosystem, maintaining a delicate balance across billions of years. They are fundamental components in vast feedback loops, acting as mediators that transfer energy and momentum from the explosive death of a single star to the evolutionary pace of an entire galaxy, ensuring a state of equilibrium. Astrophysicist Dr. Liu Zhang remarks that feedback loops with shockwaves are the universe's thermostat, preventing runaway star formation or quenching it to sustain long-term structure growth. This regulation unfolds through a constant push and pull between creation and suppression. On one hand, a shockwave from a supernova can compress a nearby gas cloud, triggering a burst of new star formation in a powerful example of positive feedback. Yet that same stellar nursery, once ignited, produces massive stars that quickly explode, their collective shockwaves driving a galactic wind. This wind can violently eject vast reservoirs of star-forming gas out of the galaxy entirely, enacting a potent negative feedback that shuts down star birth for eons. This process is dramatically amplified by active galactic nuclei, where shockwaves from the supermassive black hole's jets and radiation launch winds that heat and displace gas on a phenomenal scale. The ejected material, rich with newly forged elements, is then recycled into the intergalactic medium, seeding future generations of galaxies with the potential for planets and life. We can observe this self-regulation within our own Milky Way. The Fermi bubbles, colossal structures of gamma-ray emission ballooning from the galactic center, are likely the remnants of an ancient shockwave-driven outflow from our central black hole. This event would have violently reshaped the gas content in our galaxy's halo, influencing which regions could collapse to form new stars and planets. How do these feedback mechanisms influence the cosmic star formation history? They are the reason star formation across the universe peaked billions of years ago and has been gradually declining since, a direct result of shockwaves systematically ejecting the fuel from galactic reservoirs. This intricate dance of triggering and quenching, governed by shockwaves, directly sets the stage for the formation of planetary systems like our own. A young protoplanetary disk swirls around a newborn star, a vast, dusty carousel of potential worlds. Then, a silent, invisible force arrives, a shockwave from a distant supernova light years away. This cosmic pressure front slams into the disk, and in its wake nothing is the same. The gentle drift of dust and ice is thrown into chaos, compressed into dense ribbons where particles collide and stick together with newfound urgency. Planetary scientist Dr. Chloe Brown describes shockwaves as the unseen midwives in the birth of planetary systems, seeding them with elements and shaping their orbital characteristics. This intervention operates through several powerful mechanisms. The initial compression wave can dramatically enhance the growth of dust grains, forcing them together so they rapidly snowball into the first planetesimals, the building blocks of planets. Simultaneously, the shock-induced turbulence acts like a cosmic whisk, thoroughly mixing volatile ices with refractory rocks, ensuring that future planets form from a well-blended recipe of ingredients. One of the most profound consequences is the delivery of short-lived radioactive isotopes like aluminum-26. This material, forged in the supernova itself and carried by the shockwave, is injected into the protoplanetary disk. As these atoms decay, they release intense heat, warming the interiors of the young planetesimals. This thermal engine can drive geological activity, melting ice to form water oceans deep within asteroids and potentially creating the conditions for early chemistry. The shock can also trigger gravitational instabilities in the disk's gas, causing it to rapidly collapse directly into gas giant planets, bypassing the slower core accretion process and explaining how some massive worlds form so quickly. Our own solar system bears the chemical scars of this process. Isotopic anomalies found in ancient meteorites point decisively to an injection of supernova material, a gift from a shockwave that swept through our cosmic neighborhood just as the Sun's planetary family was taking shape. How common are shockwave-triggered planetary systems in the galaxy? This might be a fundamental step for birthing rocky worlds rich with the elements for life. Just as shockwaves sculpt the dense nodes of the cosmic web, they also play a role in defining the vast, empty expanses between them. Drifting through the cosmic web are the great voids, immense and nearly empty regions separating the brilliant filaments of galaxies. These are the deserts of the cosmos, but they are not completely barren, nor are they silent. Cosmologist Dr. Nathan Cole explains that voids are not entirely empty. Shockwaves from neighboring clusters can send ripples through them, subtly shaping their boundaries and internal properties. The same titanic forces that build the dense nodes of the cosmic web also reach out to sculpt these vast expanses of nothing. As shockwaves from colossal cluster mergers and galactic superwinds propagate outwards, they eventually encounter the tenuous gas within a void. The interaction is subtle but profound. A shock front does not slam into a dense wall here. Instead, it pushes against a sparse fog, and this gentle, persistent pressure can drive the already diffuse gas further outward, effectively helping the void to expand and evacuate even more over cosmic time. This process carves the voids into their distinct, often spherical shapes, and can even generate internal substructure. The shockwave's passage may compress isolated pockets of that sparse gas, triggering rare and unexpected bursts of star formation in the few, lonely galaxies that reside within the void, their solitary lights flickering on in the profound darkness. We can see a potential example of this in the Boötes void, a colossal empty region where the distribution of its handful of galaxies suggests they may have been influenced by shock-induced pressures from the surrounding superclusters. How do shockwaves contribute to the uniformity or irregularity of void networks? They likely act as cosmic chisels, refining the edges of these empty bubbles and contributing to the overall honeycomb-like pattern of the universe. These ripples through emptiness leave faint observational signatures, minute distortions in the maps created by vast redshift surveys that track the positions of millions of galaxies. By analyzing the peculiar motions of galaxies on the void boundaries, astronomers can infer the history of these gentle shocks. This understanding of how shockwaves shape both the full and the empty brings our journey to the edge of the observable universe, to a time when the first structures were just beginning to spark against the darkness. Light from a quasar piercing the cosmic dawn carries more than just brilliance. It holds a hidden record of violence. At redshifts greater than 6, when the universe was less than 1 billion years old, the first galaxies and quasars were already generating immense shockwaves that ripped through the thin intergalactic medium. These ancient disturbances left permanent scars in the light from distant quasars, etched as absorption lines in their spectra that we can decode today. Studying these high-redshift shockwaves provides a direct probe into the universe's tumultuous youth, revealing the intensity and frequency of the earliest astrophysical cataclysms. Dr. Isabella Rossi describes these shockwaves as time capsules, preserving the conditions of the cosmos when structures were just beginning to assemble. The primary evidence comes from the Lyman alpha forest. The complex pattern of absorption lines created as quasar light passes through clouds of neutral hydrogen. When a shockwave passes through such a cloud, it superheats the gas and stirs it into turbulence. This motion manifests as a distinct broadening of the absorption lines, a telltale smearing that signals the passage of a powerful pressure wave billions of years ago. In some rare cases, astronomers have also detected faint, extended halos of X-ray emission around primordial galaxies, a signature of gas heated to millions of degrees by ongoing shock activity from stellar winds and supernova. Observing these phenomena is incredibly challenging. The signals are exceedingly faint, stretched and diluted by the expansion of the universe over immense distances. Detecting them requires the extreme sensitivity of next-generation telescopes like the James Webb Space Telescope and the upcoming extremely large telescopes, instruments designed to gather the whispers of the infant cosmos. Interpreting the data adds another layer of complexity, as the signals must be untangled from the complex backdrop of the Reionization era, when the universe was still being flooded with ultraviolet light. A compelling example is found in the outflows of a high-redshift quasar, where shockwaves are inferred from the enormous velocity spreads in its emission lines. The gas is moving so fast with such disorder that only a powerful shock can explain its behavior. What can these high-redshift shockwaves tell us about the initial mass function of the first stars? Their strength and prevalence suggest that the earliest stellar generations were dominated by colossal, short-lived stars, whose violent death seeded the young cosmos with powerful waves and heavy elements. This focus on the most ancient shocks naturally leads us to consider their role in the continuous journey of cosmic material, the great Baryon cycles that govern the evolution of all galaxies. This great cosmic conveyor belt of ordinary matter, the Baryon Cycle, turns ceaselessly across the cosmos. Its engines are the very shockwaves that course through the vast spaces between galaxies, tirelessly moving gas from the intergalactic medium into galactic halos and back out again. Without this constant churning driven by immense pressure, galaxies would either starve, quickly exhausting their fuel for new stars, or drown in their own unmixed, unprocessed gas. Astrophysicist Dr. Ryan Kim remarks that shockwaves power the Baryon cycle, ensuring that gas is continually processed and redistributed, fueling star formation and enriching environments. They are the fundamental motors that regulate the growth and evolution of every galaxy we see. This process unfolds through 3 key mechanisms, all governed by the push and pull of these cosmic waves. First, consider gas accretion, the way fresh fuel falls into a galaxy's gravitational embrace. Shockwaves from cosmic structure formation create powerful pressure gradients in the circumgalactic medium, the vast gaseous atmosphere surrounding a galaxy. These pressure differences can literally funnel cool gas streams directly into the galactic disk, providing a steady supply of pristine hydrogen. Simultaneously, the same shockwaves can heat other portions of this gas to extreme temperatures. This shock-heated gas must then cool and condense over millions of years, eventually raining down into the galaxy in a slower, more gradual manner. Look at our own Milky Way. Its halo is not a static void but a dynamic reservoir. Shock-induced accretion from the intergalactic medium and from smaller, cannibalized satellite galaxies constantly supplies our galaxy with fresh gas, replenishing the raw material needed for future generations of stars. Second, shockwaves are the primary force behind the ejection and recycling of this precious material. When a burst of supernova or an active galactic nucleus goes off, the resulting shockwaves launch powerful galactic winds. These winds do not simply vanish, they carry enriched gas far out into the circumgalactic medium, where it is mixed and churned by turbulent shocks. This turbulent mixing is crucial. It disperses heavy elements forged in stellar cores uniformly throughout the galactic environment, ensuring that the next cycle of star formation has a richer, more complex chemical palette to work with. How do shockwaves affect the efficiency of baryon conversion into stars? They are the universe's method of resource management, determining how much gas is turned into suns versus how much is stored for later or expelled entirely. This regulation creates a delicate feedback loop where too much shock-driven ejection can quench a galaxy, while too little leads to inefficient consumption. This entire cycle, from accretion to wind-driven recycling, is fundamentally intertwined with the nature of cosmic turbulence, a chaotic force that shockwaves both generate and are shaped by. The cosmos churns with a turbulence that makes the most violent ocean storm seem placid. Shockwaves are the great storms of this cosmic sea, their immense fronts stirring the primordial gases into a frenzy of eddies and currents that mix materials and transfer energy across vast scales. Fluid dynamicist Dr. Mei Lin describes this relationship by saying, "Turbulence seeded by shockwaves is the universe's mixer, homogenizing densities and temperatures while enabling complex phenomena like star formation." These waves are not just events, they are engines of chaos, injecting raw power into the interstellar and intergalactic medium and fundamentally shaping how gas behaves. This process is governed by the theory of turbulent cascade. A single shock wave from a supernova injects a colossal amount of energy at a large scale, creating massive swirls and ripples. These large eddies then break down, transferring their energy to progressively smaller and smaller scales in a cascading waterfall of motion, until that energy finally dissipates as heat or drives the subtle motions of tiny gas clouds. This turbulent energy has several profound effects. First, it can provide a form of support within molecular clouds. The chaotic, churning motions generated by passing shockwaves create an internal pressure that helps the cloud resist its own gravity, effectively slowing down the process of collapse and regulating the pace at which new stars are born. Second, this turbulence dramatically enhances magnetic reconnection. It twists and braids magnetic field lines, forcing them together in ways that can explosively release stored energy, a process that can heat surrounding plasma and accelerate particles to high speeds. We can observe the fingerprints of this shock-driven turbulence in the emission lines from distant nebulae. The light from these clouds does not come out at a single, pure wavelength. It is smeared out or dispersed because the gas is moving in all directions at once within the turbulent flow. A clear case study is the Taurus molecular cloud, a nearby stellar nursery. Here, observations show that shock-induced turbulence is actively sculpting the densest cores where stars are forming. influencing their final masses and potentially determining how many stars a single cloud can produce. How does turbulence from shockwaves influence the lifetime of molecular clouds? This constant churning can either prolong a cloud's existence by supporting it against collapse, or it can tear the cloud apart prematurely, dispersing its star-forming material back into the galactic cycle. This intricate relationship between shock, turbulence, and structure has a surprising consequence. It subtly warps the very space through which we measure the cosmos, influencing how we gauge the vast distances between celestial objects. That brilliant flash of a Type Ia supernova serves as a cosmic mile marker, a so-called standard candle used to measure the vast expanses of the universe. Yet this apparent reliability can be subtly compromised by the very shockwaves these explosions create. Cosmologist Dr. Paul Evans describes shockwaves as subtle gremlins in the machinery of cosmology, sometimes distorting the signals we rely on to map the universe's expansion. These waves introduce uncertainty into our most fundamental cosmic measurements, potentially biasing our understanding of the universe's growth and composition. Primary mechanism involves the supernova event itself. A Type Ia supernova is thought to occur when a white dwarf star reaches a critical mass, but the surrounding environment matters immensely. If the progenitor system is bathed in the shockwave from a previous stellar event, or if the supernova's own blast wave interacts with dense, pre-existing circumstellar material, the resulting light curve can be altered. The shock interaction can deposit extra energy, making the supernova appear brighter or causing its brightness to decline at a different rate. Since astronomers calibrate distance based on the assumed peak luminosity, a shockwave-boosted supernova could be mistakenly calculated as being closer than it truly is. This directly impacts the calibration of the cosmic distance ladder. Another critical area is the distortion of the cosmic microwave background's acoustic scales. Those frozen sound waves from the early universe provide a standard ruler, but the passage of later shockwaves through the intergalactic medium can slightly warp this ruler by creating large-scale inhomogeneities. These density variations act as weak lenses, minutely deflecting the CMB photons on their journey to us and subtly scrambling the pristine pattern. When studying dark energy through distant supernova, even a small systematic error of this kind can lead to significant miscalculations in the inferred strength of this mysterious force. A clear illustration of this challenge is found closer to home within our own galaxy. Astronomers sometimes use expansion parallax to measure the distance to supernova remnants, tracking the apparent growth of the shock front against the sky. However, if the shockwave is plowing into a region of uneven density, it will expand at different rates in different directions, making the distance measurement unreliable. How can we account for shockwave effects to improve the precision of our cosmic maps? The answer lies in developing more sophisticated models that simulate these interactions, and in cross-referencing distance measurements from multiple independent methods. This intricate challenge of interpreting light is now being transformed by the arrival of entirely new cosmic messengers. On August 17, 2017, the universe sent us a message written in ripples of space, time, and light. For the first time, observatories detected both gravitational waves and a brilliant flash of gamma rays from the same event, a pair of neutron stars colliding in a distant galaxy. The resulting kilonova was a cosmic forge, its violent shockwaves blasting out a cloud of material rich with newly minted gold, platinum, and other heavy elements. This event, known as GW 170817, marked the dawn of multi-messenger astronomy, a field where shockwaves are no longer inferred but directly witnessed through multiple cosmic signals. Astrophysicist Dr. Sanjay Patel explains that multi-messenger astronomy turns shockwaves from hidden players into headline acts, allowing us to witness their roles in real-time cosmic dramas. Now we can observe a single cataclysm through different lenses, each messenger revealing a unique facet of the shockwave's power. Gravitational waves carry the imprint of the asymmetric collapse and merger that generates the initial shock. A neutrino burst, often the very first signal to escape, is produced when a shockwave breaks through the surface of a collapsing star. The subsequent electromagnetic fireworks, from gamma rays to visible light, are born in the expanding shock front as it slams into surrounding material and accelerates particles. The synergy is transformative. By combining the data, scientists can tightly constrain the shock's energy, speed, and geometry. The gravitational waves tell us about the initial engine, the neutrinos reveal the conditions at the moment of shock breakout, and the light across the spectrum shows us the aftermath and the elemental production line. This combined view offers unprecedented insights into particle acceleration, showing exactly how these natural accelerators can push particles to energies far beyond anything we can create on Earth. It also probes extreme physics, testing matter under conditions of density and pressure that simply cannot be replicated in a laboratory. In the case of GW 170817, the shockwaves from the merger did not just create a kilonova. They also produced a long-lasting afterglow as the ejected material plowed into the interstellar medium at relativistic speeds, a fireball observed by telescopes from radio to X-ray wavelengths. What new shockwave phenomena might multi-messenger observations unveil in the next decade? As our detectors become more sensitive, we may witness the birth of a supernova through neutrinos and gravitational waves moments before its light reaches us, or detect the shockwaves from a cosmic string snap, events that would illuminate the most fundamental laws of physics. This holistic view of cosmic violence reveals the direct link between these immense pressure waves and the very elements that make up our world. The universe's periodic table was not forged all at once, but written in successive waves of cosmic violence. Over billions of years, shockwaves from countless stellar explosions have acted as the great distributors, scattering newly minted elements like oxygen, silicon, and gold into the void. This gradual enrichment, increasing the metallicity of cosmic gas, transformed a primordial universe of hydrogen and helium into one capable of complex chemistry and planets. Astrochemist Dr. Olivia White calls shockwaves the universe's alchemists, transforming simple elements into complex molecules and distributing them across cosmic epochs. Their role is threefold. They disperse the products of nucleosynthesis, they violently mix these elements into the interstellar medium, and they directly influence the chemical patterns we observe in the atmospheres of ancient and modern stars. This dispersal is not a gentle sprinkling, it is a forceful injection. A supernova shockwave does not just carry heavy elements, it propels them at tremendous speeds, ensuring they travel far from their birthplace and penetrate deep into neighboring molecular clouds. The shock front itself can trigger fascinating chemistry, its immense pressure either forging new dust grains from gaseous atoms or shattering existing ones, a cycle of creation and destruction that constantly resets the granular makeup of space. Furthermore, the turbulent wake of a shockwave acts as a perfect cosmic blender, churning different elemental strands together to achieve a more uniform mixture, a process essential for creating the consistent chemical recipes we see in later generations of stars. We can trace this evolutionary story by comparing different stellar populations. The ancient population 2 stars found in the galactic halo show very low metallicity, their atmospheres pristine records of a time before shockwaves had widely seeded the galaxy with heavier elements. In contrast, younger population 1 stars like our Sun are metal-rich, their composition reflecting billions of years of progressive enrichment by shockwaves from countless supernovae. This history is written in the subtle abundance ratios found in stellar atmospheres. A compelling clue comes from the carbon-enhanced metal-poor stars. These ancient celestial bodies possess surprising amounts of carbon despite their overall low metal content, a peculiar signature that may point to enrichment from the very first supernova, whose unique shockwaves scattered specific patterns of elements across the early cosmos. How do shockwaves contribute to the diversity of chemical environments in galaxies? They ensure that some regions become fertile grounds for organic chemistry, while others remain elemental deserts, directly influencing where and how life might eventually arise. This grand narrative of chemical evolution, driven by relentless waves of pressure, finds its ultimate connection in the universe's first moments, tying the alchemy of stars directly to the relics of cosmic inflation. Fossils from the universe's explosive birth lie scattered throughout the cosmos, and shockwaves were the excavators that uncovered their secrets. These relics, like primordial black holes or cosmic strings, are theorized remnants from the inflationary epoch, the universe's first fleeting moment of existence. Theoretical physicist Dr. Victor Orlov notes that inflation relics and shockwaves are intertwined threads in the cosmic tapestry. Studying their interactions can reveal hidden dimensions of early universe physics. These ancient shockwaves did not create the relics, but they fundamentally reshaped their distribution and visibility, acting as a cosmic tide that either gathered these fossils into clusters or scattered them into obscurity. Imagine a field of ancient bones buried just beneath the surface. A sudden and powerful flood then sweeps through, washing away the soil in some areas and piling it high in others, completely altering the pattern of where the bones are found and how easily they can be seen. This is the role shockwaves played with inflation's artifacts, a network of cosmic strings, hypothetical one-dimensional defects in space-time, could have been jostled and organized by the passage of immense pressure waves, their delicate vibrations potentially amplified into faint gravitational signals we might one day detect. Similarly, shockwaves from early phase transitions could have swept through regions of space, dissipating fragile domain walls or causing clusters of primordial black holes to merge, their violent collisions sending new ripples through space-time. This interaction has profound implications for our search for these elusive objects. The expected abundance of certain relics, used by cosmologists to rule out various models of inflation, might be completely revised if we account for the sweeping and clustering effects of shockwaves. What signatures of inflation relics might be enhanced or obscured by shockwave activity? A relic that appears too rare might simply have been efficiently hidden by ancient cosmic tides. Furthermore, the turbulent motion stirred by these shocks could have generated a secondary background of gravitational waves, a faint hum layered over the primordial signal from inflation itself. Certain models suggest that when the bubbles of a new cosmic phase collisioned at the end of inflation, the resulting shockwaves produced a gravitational wave background with a specific frequency, a signal that next-generation observatories are actively hunting. This intricate dance between relic and shock even touches upon the mystery of dark matter, as some candidates, like certain types of primordial black holes, could have had their distribution and thus their observational signatures permanently altered by these forces. Understanding how shockwaves rearranged these primordial fossils provides a crucial key, not just to the universe's first moments, but also to the tools we use to measure its subsequent expansion. That ancient star in the halo of our Milky Way may not be the reliable clock we once believed. Astronomers use such celestial objects as cosmic chronometers, carefully measuring their composition to date pivotal events in universal history. Yet a single shockwave from a primordial supernova could have fundamentally altered the very evidence we rely on. Cosmochronologist Dr. Hannah Green describes shockwaves as the wild cards in cosmic dating, sometimes preserving and other times scrambling the records we rely on for timing the universe's history. Their influence introduces a layer of uncertainty into our most fundamental timelines. The disruption occurs through several distinct mechanisms. A shockwave can trigger a burst of star formation earlier than models predict, which then pollutes the interstellar environment with metals sooner than expected. When we later find an ancient metal-poor star, we might mistakenly assign it a more advanced age, not realizing its pristine atmosphere was actually contaminated by shockwave-driven enrichment from a nearby cataclysm. This directly affects the age-metallicity relation, a key tool used in galactic archaeology to reconstruct our galaxy's formation history. Even more direct is the effect on isotopic clocks. Short-lived radioactive isotopes like aluminum-26 serve as precise chronometers when trapped in meteorites. A shock wave can inject a fresh wave of these isotopes into a forming planetary system, effectively resetting the decay clock and making the system appear younger than it truly is. Consider the oldest stars in the Milky Way's halo. Their bizarre abundance patterns with surprising amounts of certain heavy elements despite an overall low metal content may not be a simple signature of the first stars. Instead, they could be the product of shockwaves from specific types of early supernova, which selectively polluted these stars' birth clouds and left a scrambled chemical message for us to decipher. This has profound implications for dating globular clusters, whose estimated ages provide a lower limit for the age of the universe itself. If shockwaves prompted some clusters to form earlier than we calculate, or with altered initial chemistries, our estimate for the universe's age could require subtle revision. How can we disentangle shockwave effects to obtain more accurate cosmic timelines? The answer lies in building more sophisticated models that simulate these turbulent interventions, comparing numerous independent dating methods to identify inconsistencies. This challenge of reading a universe shaped by violent waves now pushes us to design observatories capable of seeing through the chaos. Silent and cold in the void, the James Webb Space Telescope aligns its golden mirrors not to capture light, but to listen for the faintest whispers of creation. It is joined by a chorus of future observatories, from the continent-spanning square-kilometer array to the proposed Lynx X-ray Observatory, all designed with an unprecedented sensitivity to the subtle signatures of cosmic shockwaves. Astronomer Dr. Liam O'Donnell believes the next decade of astronomy will turn shockwaves from theoretical curiosities into observational staples, thanks to instruments that see farther and clearer than ever before. These are not merely incremental improvements, they are revolutionary leaps that will transform our understanding of these formative forces. The James Webb Space Telescope, with its powerful infrared eye, will peer into the hearts of high-redshift galaxies to directly image the shock-induced outflows that cleared the primordial fog. It will analyze the chemistry of ancient gas clouds, looking for the unique elemental fingerprints left by the shockwaves from the very first supernova. Meanwhile, the square-kilometer array will function as a colossal radio ear, listening to the faint, low-frequency hum of synchrotron radiation. This will allow it to map the vast, invisible shock fronts that ripple through galaxy clusters, tracing their structure with a clarity we have never before achieved. The synergy between these tools is what promises true discovery. A shock wave detected by its radio signature with the SK can be followed up by Webb to study how it has influenced the gas and stars within a galaxy, providing a complete picture of its impact. Expected advances from this new era of observation are profound. we will move from seeing a few textbook examples to mapping the full distribution of shocks throughout the cosmic web, understanding how they channel energy and matter along its filamentary strands. We will search for the faint, swirling patterns in the cosmic microwave background's polarization, the B modes that could hold the imprint of primordial shockwaves from the universe's first violent phase transitions. And we will combine this electromagnetic data with alerts from gravitational wave detectors, creating a multi-messenger portrait of the most energetic events, where shockwaves are born from the collisions of neutron stars and black holes. The LINX X-ray observatory concept exemplifies this new power. Designed to see with exquisite X-ray vision, LINX could directly image the sharp shock fronts in young, forming galaxy clusters, watching in real time as they heat gas and regulate the growth of these colossal structures. What surprises might these new tools reveal about the hidden role of shockwaves? We may find that they were even more prevalent and powerful than our models suggest, or discover entirely new classes of cosmic disturbances that challenge our fundamental assumptions. This impending flood of data does not just promise new facts, it invites us to reconsider our very place within the grand, turbulent narrative of the cosmos. These immense waves are more than cosmic phenomena, they are fundamental threads in the fabric of reality itself. Their study pulls us from pure physics into deep philosophical waters, challenging our very ideas of chance and destiny in a universe built by violence. Understanding shockwaves forces us to reconsider concepts like causality and fine-tuning, for these seemingly chaotic events produce profoundly directed and creative outcomes. The philosopher of science, Dr. Elena Morau, reflects that shockwaves remind us the cosmos is not a static artwork but a dynamic performance, where chance and necessity dance together to create complexity. This dance is visible everywhere we look. The random collapse of a star in one galaxy sends out a shock front that, millions of years later, triggers the birth of a solar system in another, a solar system that may one day harbor life. This is not a linear chain of cause and effect, but a web of stochastic possibility, where disorder gives rise to intricate order. This interplay between chaos and structure raises profound questions about our own existence. The heavy elements forged and scattered by shockwaves are the very ingredients of planets and living organisms. Our own biological reality is a direct consequence of these ancient, violent events, linking the fury of a supernova to the air in your lungs. This cosmic interconnectedness carries its own ethical dimension, a reminder that we are not separate from the universe's turbulent processes but are utterly woven from them. It inspires new paradigms, urging scientists and artists alike to see creativity not as a gentle process, but as a forceful, transformative act. Do shockwaves suggest a universe that is inherently creative or destructive? The answer seems to be both, a cycle where each act of annihilation clears the stage for a new act of creation. This perspective shifts our place in the cosmos from passive observers to active participants in an ongoing, dynamic story. Our journey reveals a cosmos sculpted by immense, invisible hands. From the first chaotic moments after the Big Bang, cosmic shockwaves acted as the hidden architects of everything we see. They carved the vast cosmic web from formless plasma, triggered the birth of the first stars within compressed gas clouds, and seeded the universe with the heavy elements essential for planets and life. Their echoes are permanently etched into the oldest light we can observe and are still detectable in the violent mergers of galaxy clusters today. This narrative shows a universe that is profoundly dynamic and interconnected, where cataclysmic events in one corner of space-time ripple across epochs to shape destinies in another. The continued study of these powerful waves is crucial, for it not only deepens our grasp of cosmic evolution, but also highlights the delicate balance of forces that allowed a habitable world to emerge from the chaos. The legendary Carl Sagan once reflected that we are made of star stuff. It is a humbling truth, for the very atoms that constitute our bodies were forged in stellar furnaces and scattered across the galaxy by shockwaves from ancient supernova. This knowledge invites us to see the night sky not as a distant tapestry, but as a part of our own extended history. We would love to hear how these cosmic connections reshape your perception of the universe, so please share your thoughts and questions in the comments below. If you want to continue exploring the profound mysteries of space with us, be sure to subscribe. Thank you for joining this incredible journey through the hidden landscapes of the early cosmos.